Hello everyone, my name is Rhea Palak Bakshi. I am a rising fifth year PhD student at the George Washington University. I would like to thank the organizers of CKVK Asterisk for giving me the opportunity to speak at their seminar and for organizing the seminar in such trying times. For those of you who are watching this video during the pandemic, I hope that you're all in good health and that you're safe at home. So today I'm going to be talking about Skein modules and framing changes of links in three manifolds. So here is the abstract. We show that the only way of changing the framing of a link by ambient isotopy in an oriented three manifold is when the manifold admits a properly embedded non-separating two sphere. This change of framing is given by the Dirac trick, which is also known as the light bulb trick. And the main tool we use is based on Daryl McCullough's work on the mapping class groups of three manifolds. We also express our results in the language of Skein modules. And in particular, we will relate our results to the presence of torsion in the framing Skein module. Okay, so let's start. Skein modules were introduced by Josef Pshutitsky in 1987. And what is a Skein module? Well, in the most general setting, a Skein module is an algebraic object associated to an oriented three manifold, and it is usually constructed as a formal linear combination of embedded or immersed submanifolds, modulo some locally defined relations. And while choosing these relations, one takes into account the following factors. First, whether the manifold we obtain is computable. Second, how well the Skein module distinguishes between three manifolds and different links in the three manifolds. Whether the Skein module reflects the topology or geometry of a manifold. For example, does the Skein module detect the existence of incompressible or non-separating surfaces in the manifold? Does it say anything about the geometric decomposition of a manifold? Or whether the Skein module admits some additional structure. For example, does it have some algebra structure? Is it a Hopf algebra? Can you categorify the Skein module and so on? So there are numerous definitions of Skein modules associated to a three manifold. But all these definitions have in common is that they try to capture some information about the knot theory that the three manifold admits. Now, the reason why we have so many definitions is because you can consider the knots and links in the manifold to be framed or unframed, oriented or unoriented, up to homotopy or up to isotopy, and so on. But what all these definitions do is that they generalize the Skein theory of the polynomial link invariants in S3, like the Jones polynomial, the Homfly-PT polynomial, the Kaufman bracket polynomial, or the Kaufman two-variable polynomial, to arbitrary three manifolds. So a Skein module is a generalization of the usual polynomial link invariance in S3 to arbitrary three manifolds. Okay. So in our talk, we will focus on whether Skein modules say anything about the existence of non-separating surfaces in a three manifold or not. Okay, usually the existence of non-separating surfaces in a three manifold reflects itself in the Skein module as torsion. So just like in Kavanagh homology, torsion is an important property because it's not present in the Jones polynomial, which it categorifies. Similarly, the presence of torsion in Skein modules is of interest to us. In 1995, Josef Pshutitsky showed that the framing sign Skein module, which is also known as the Q deformation of the fundamental group, has torsion in the manifold, has torsion if the manifold contains non-separating tori and two spheres. He also showed that the presence of non-separating closed surfaces in an oriented three manifold yields torsion in the Q homology Skein module. The Kaufman bracket Skein module also has torsion if the three manifold contains non-separating spheres and tori, and this torsion is yielded by the light bulb trick, which I will talk more about later in the video. And the goal for today's talk is to understand the structure of the framing Skein module and check whether it detects the presence of non-separating surfaces in an oriented three manifold. Okay. So here's the outline of my talk. First, I'll talk about some preliminary notions about the mapping class group of three manifolds and Dehn homeomorphism. Then I will talk about Daryl McCullough's work on homeomorphisms, which are Dehn twists on the boundary. Then I will talk about our main results and provide their proofs. And then I will relate our results to the framing Skein module. And finally, I will talk about connections to other Skein modules, in particular the Kaufman-Brackes Skein module and the Q-homology Skein module, and talk about future directions. This is joint work with Joni Ibarra, Gabriel Montoya Vega, Josip Chititsky, and Deborah Weeks. All right. So here's the definition of a compressing disk. So let F be a properly embedded surface in a 3-manifold, or be a boundary of or be a part of the boundary of the manifold. Then a disk D2 in M is called a compressing disk of F if the intersection of this disk with the surface is the boundary of the disk and the boundary of the disk is not contractible in F. An embedded surface F in M that admits such a compressing disk is said to be compressible. If the surface is not the two-sphere or the disk and it contains no compressing disk, then the surface is said to be incompressible. If the surface is the two-sphere, then F is said to be incompressible if it does not bound a 3-ball in M. Okay. Here's a definition of the mapping class group of a manifold. So the mapping class group of an orientable manifold is the space of all ambient isotopy classes of the group of PL orientation preserving homeomorphisms of the manifold. So that is the mapping class group. And here are two important theorems about the mapping class group of a manifold. The first is the finite mapping class group theorem. The statement presented here is actually a combination of results by various authors mentioned. And the theorem says that if M is a closed-oriented, irreducible, non-Harkin 3 manifold, then the mapping class group of that manifold is finite. And the second theorem, due to Gabay, Meyerhoff, and Thurston, says that the mapping class group of a compact hyperbolic 3 manifold is finite. Okay, so this brings us to the definition of a Dehn homeomorphism. So you consider an n-dimensional manifold M and a codimension 1 submanifold F, such that F times I intersected with the boundary of this manifold is simply the boundary of F times I. And then you consider an element of the fundamental group of the space of PL orientation preserving homeomorphisms of F, phi T, and you define a Dehn homeomorphism to be an element of the mapping class group defined as follows. So if xt belongs to F times I, then the Dehn homeomorphism is simply phi T x comma T. And if an element does not belong to F times I, then H of that element is simply that element. Okay, so we see that Dehn homomorphisms are generalizations of Dehn twist homomorphisms of a surface. And one thing to note is that the fundamental group, that if the fundamental group of homeo F, so if the fundamental group of the space of orientation preserving homomorphisms, PL orientation preserving homomorphisms is trivial, then the Dehn homomorphisms must be isotopic to the identity. And as a side remark, the Dehn subgroup, which is also known as the Johansen subgroup of the mapping class group, is the subgroup generated by all Dehn homeomorphisms. So to make it more clear, here is a table of Dehn homeomorphisms of 3 manifolds for these surfaces. And these are the corresponding Dehn homeomorphisms. So for our talk, we will focus on Dehn homeomorphisms, which are Dehn twists about the annulus, twist about the disk, and rotation about a sphere. Okay. So now this brings us to two important theorems by McCullough. The first one is that if M is a compact orientable 3 manifold which admits a Dehn homeomorphism on the boundary about a collection of simple closed curves on the boundary, then each of these simple closed curves bounds a disk in M, or a pair of these simple closed curves co-bounds an incompressible annulus in M. And an immediate corollary of this is as follows. If you have a compact oriented 3 manifold, one of whose boundary components is a torus, and say you don't know this torus by boundary knot M prime, and you have F tilde, which is a self-homeomorphism of this 3 manifold, which acts non-trivially on this boundary torus, and it's constant on the complement, then this torus contains a compressing disk. Okay, so one thing I want to call attention to is that I have mentioned M prime here instead of M. The reason will be clear when I discuss the proof of the main result. So for now, just think of any compact oriented 3 manifold, but keep in mind that this M prime is going to turn up later on in the talk. Okay. So the next theorem by McCullough is as follows. So you consider, again, a compact orientable 3 manifold, which admits a Dehn homeomorphism on the boundary about a collection of simple closed curves in the boundary of M. Then there is a collection of disjoint embedded disks and annuli in M, each of whose boundaries is isotopic to one of these simple closed curves, for which some composition of Dehn twists about these disks and annuli is isotopic to the Dehn homeomorphism on the boundary of the manifold. And the key thing to take from this theorem is the following corollary, which says that just as before, if you have a compact oriented 3 manifold with some boundary components being tori, and again you have F tilde, which is a self-homeomorphism of M prime, which acts non-trivially on these tori, but is the identity on the complement, then either these boundary tori have compressing disks, or there is an incompressible annulus with one boundary component on one boundary torus and the other boundary component on another boundary torus. And furthermore, you can take these disks and annuli to be disjoint. Moreover, F tilde restricts to boundary of M prime. Sorry, F tilde restricted to boundary of M prime is ambient isotopic to the composition of some powers of the Dehn homeomorphism along these compressing disks and incompressible annuli. So the reason why these two corollaries are important is because they tell us that if we have a compact oriented 3 manifold with a Dehn homeomorphism as described on the boundary, then there exist compressing disks and incompressible annuli which are disjoint. And these compressing disks and incompressible annuli are important because they form the building blocks of the non-separating two spheres in the 3 manifold. Okay. All right. So this brings us to our main result. So the theorem says that if L is a framed link in a compact oriented 3 manifold M, then the only way of changing the framing of L by ambient isotopy while preserving the components of L is when the manifold has a properly embedded non-separating two sphere. And either this framed link intersects the non-separating two sphere transversely exactly once, or it intersects the non-separating two sphere transversely at 2 points, each point belonging to a different component of the link. The framing change is given by a composition of even powers of the Dehn homeomorphisms along the disjoint union of these non-separating two spheres which satisfy these two conditions. And the framing change is illustrated and or rather it's given by the Dirac trick or the light bulb trick. So in the first case, where the non-separating two sphere is intersected once by the frame link, we have the usual Dirac trick or light bulb trick. So this red line segment illustrates a section of a component of the framed link L which intersects the non-separating two sphere once. And then this sequence of ambient isotopies gives this figure on the bottom left. And notice that the framing of L has changed by +2. Okay, and in the second case, where the non-separating two sphere is intersected twice by the framed link, we have the following diagram. So we have the following light bulb trick where we have K1 and K2. There are two components of the framed link L which intersect the non-separating two sphere once each, and then this sequence of ambient isotopies gives us this figure on the bottom left. And the key thing to note is that the framing of K1 is changed by +2, but the framing of the second component is changed by -2. Okay, so let's prove this theorem. So first, we're going to prove the following lemma, which says that if L is a framed link in a compact oriented three-manifold M, and F is a self-homomorphism of M, which changes the framing of L while preserving the components of L, and F restricted to the boundary of M is the identity, then there is a non-separating two-sphere in M, and either the frame link intersects the non-separating two-sphere once, or it intersects the non-separating two-sphere transversely in 2 points, each point belonging to a different component. And the framing change is given by a composition of powers of Dehn homomorphisms or rotations along the disjoint union of the non-separating two spheres that satisfy these two conditions. Okay, so let's proceed with the proof. So here's an outline of the proof of the lemma. So without loss of generality, we can assume that the homeomorphism F changes the framing of all the components of the framed link L, and we'll denote these components by K sub I. Okay. Some notation. So VKI denotes the regular neighborhoods of the components Ki, and then mu I would be the meridian of the regular neighborhood. M prime is the complement of the union of the interiors of the regular neighborhoods of these components in M. And F tilde is the restriction of M to M prime. So notice that this M prime and F tilde are exactly what we had in the two corollaries that I discussed before. Okay, so from the first corollary, for each I, there is a compressing disk of boundary VKI, or there exists an incompressible annulus with one boundary component on one of the boundary VKIs and the other on another boundary VKJ. All right. And by the second corollary, these compressing disks and incompressible annuli are disjoint. And if you recall, these compressing disks and incompressible annuli are now the building blocks of our non-separating two spheres, and this is how we construct them. Okay, so first we note that the Dehn twists about the compressing disks and the meridian disk of VKI are exactly the same. Otherwise, F tilde cannot be extended to F. And this implies that the boundary of the compressing disk is the same as the boundary of this meridian disk. And then when you glue them along their boundaries, you get a non-separating two sphere, which is intersected by Ki, the component Ki, exactly once transversely. Similarly, you can do the same thing for the annulus. So one boundary component of the annulus is the boundary of this meridian disk, and the second boundary component is the boundary of this meridian disk. And then when you glue the boundaries of the annulus along with the boundaries of these disks, then you get another non-separating two sphere in M, which is intersected by Ki and Kj transversely at 1 point each. Okay, so this is how we, how the non-separating two spheres are constructed. And then the action of F tilde on the boundary tori is the same as that given by some composition of Dehn homomorphisms along disjoint compressing disk and incompressible annuli. This is from the second corollary. Okay. So what we have done is that we have shown the existence of these non-separating two spheres, which are intersected either once by a component of the link or twice by a link, but then each point belongs to a different component. Okay. So one remark to this proof is that the result of this lemma can be deduced immediately if the mapping class group of M prime is finite. This is because F restricted to boundary VKI has infinite order in the mapping class group of the boundary torus. And thus F tilde has infinite order in the mapping class group of M prime. And this is a contradiction because we assumed that the mapping class group of M prime is finite. And this happens when M prime is a hyperbolic three-manifold or a closed-oriented irreducible non-Haken three-manifold. This is from the two theorems about mapping class groups that I had discussed earlier in the video. Okay, so this is our main theorem. We revisited. So what we have shown is that The incompressible annuli and the compressing disks are the building blocks of the two spheres which are intersected either once or twice by the framed link. And the framing is changed by a composition of powers of Dehn homeomorphisms along the disjoint union of these non-separating two spheres. So the only thing left to show is that these Dehn homeomorphisms are actually that even powers of these Dehn homeomorphisms are isotopic to the identity. And we are going to show that now. Okay, so here's a proof of the theorem. So assume that the Dehn homomorphism about Si, which is the non-separating two sphere which is intersected once. So we assume that the Dehn homomorphism about Si is tau I, and that the Dehn homomorphism about Sij is tau Ij. Okay, then the fundamental group of the 3D rotation group is Z2. And so tau I square and tau Ij square are ambient isotopic to the identity map, and they realize the light bulb trick. So this will be a little more obvious when I discuss spin structure a little later. And since the function f, which changes the framing of L, is a composition of powers of these Dehn homeomorphisms, so f also turns out to be ambient isotopic to the identity map. All right. And the only thing left to show is that that f is in fact a composition of even powers of these Dehn homeomorphisms, and this is due to the existence of spin structure on every oriented 3 manifold. So what this actually implies is that the framing of a link cannot be changed by an odd number of full twists by ambient isotopy. Okay, it can only be changed by an even number. So if we look at the following diagram, so we just revisit this. Tau Ij square changes the framing of K1 by 2 and the framing of K2 by -2, right? Okay, so we will discuss spin structure and prove the remainder of the theorem. So here's the definition of a parallelizable 3-manifold. A 3-manifold M is parallelizable if the tangent bundle of M is trivial, which means that there are 3 vector fields which form a basis at every tangent space. By a theorem due to Stiefel from 1935, every orientable 3-manifold is parallelizable. So what we have is that homotopy classes of parallelizations can be identified with spin structures, and spin structures form an affine space over the first cohomology of M with Z2 coefficients. Also, every frame knot represents an element of the first homology of M with Z2 coefficients. And to every frame knot, you can associate an element of the fundamental group of the 3D rotation group, which is Z2, using the parallelization of M. And in fact, this map is a homomorphism. So for every frame knot, you have a homomorphism from the first homology to Z2. And then by the universal coefficient theorem, the first cohomology is isomorphic to the home group. Okay, so this diagram will illustrate this fact. So what we do is that we fix an orthonormal parallelization of M, say capital V1, V2, and V3. And then you consider a point P on the manifold. And due to the parallelization, you have 3 vectors belonging to these 3 vector fields respectively, incident at P. And now you consider the knot in the 3 manifold, and say you have a point Mi on the knot. And then VFR is the framing vector. This vector VT is the vector which determines the direction of travel along the knot. And then V3 prime is the unique vector which is orthonormal to both of these vectors. Okay, so these 3 vectors V1, V2, V3 are orthonormal because we consider an orthonormal parallelization. Okay, so we have a map GI which lies in SO3, which takes these 3 vectors to these 3 vectors. And then we travel along the knot and say we come to the point MJ. And then we have another map GJ in SO3, which maps these 3 vectors to these 3 vectors again. So what we have is that as we travel along the knot K, at each point or for each point on the knot, we have a map GK in SO3, which maps this vector system to a vector system incident at a point on the knot. And then when you travel along the knot, what you get is actually an element in the fundamental group of SO3, which is Z2. And so what you have is that, and so what you actually constructed was a map from the first homology of M with Z2 coefficients into Z2. And thus, the framing of a link in M can only be changed by an even number of full twists. Okay. All right, so some remarks to the theorem. So the first is that if M is an integral homology sphere or a rational homology sphere, then every knot in M has a preferred framing or a rational framing, which you can't change. And if M is a manifold which can be embedded in a rational homology sphere, then every knot in it has a preferred rational framing depending on the embedding. And you cannot change this framing by ambient isotopy again. One thing to notice, however, is that this does not apply if M has a properly embedded non-separating closed surface, since then it cannot be properly embedded in any rational homology sphere. Okay, our results also hold for non-compact tree manifolds. The reason being that the ambient isotopy of M, which changes the framing of L, can be taken to have support on a finite number of 3 balls in M. The reason, this is a result due to Hudson. So what we have is a new ambient isotopy, which has a compact oriented 3 manifold as support, and then a result follows. Okay. So this brings us to Skein modules. So we first discussed the framing Skein module. So what is the framing Skein module? Well, you consider linear combinations of ambient isotopy classes of unoriented framed links in an oriented 3 manifold, modulo framing expressions of the form L1 minus QL. Here, L1 is a framed link which is obtained from L by twisting the framing of L by 1 full twist. So if you mod out by these framing expressions, you obtain the framing Skein module. And our result is that the structure of the framing Skein module is completely determined. In particular, it detects the presence of non-separating 2 spheres in an oriented 3 manifold in the way of torsion. And in particular, the framing Skein module equals this formula on the right-hand side of the equation, where LF is composed of links which do not intersect any 2 sphere in M transversely at exactly 1 point. Now, in the theorem, we also had 2 spheres which are intersected at 2 points by the frame link, but they are not included in this theorem. The reason being as follows. So this is the proof of the theorem. So if you remember, we had 2 cases. The first being that the non-separating 2 sphere is intersected once, and the second was that the non-separating 2 sphere is intersected twice. So we'll discuss each case. So in the first case, if L intersects SI at 1 point, and say KI is the component that intersects SI, and say tau I is the Dehn homeomorphism about SI, and tau I squared is ambient isotopic to the identity, and twist the framing of KI by 2 full twists. Yeah, and that's also the framing of L. So what we have is this framing expression in the framing Skein module. And then because of this, if you change the framing twice of Ki, then we get this expression. But this is the same as applying tau I squared to Ki. So we have this framing expression. But then tau I squared is ambient isotopic to the identity. So we get the 1 minus Q square Ki is equivalent to 0 in the framing Skein module. Therefore, we get that Q square minus 1L is 0 in the framing Skein module. And so when we mod out this module by this relation, we get the result in the theorem. Okay, now we discuss the second part, where this non-separating 2 sphere Sij is intersected twice by the framed link L, once each by the components Ki and Kj. And assume that tau ij is the Dehn homeomorphism about this non-separating 2 sphere, such that tau ij squared changes the framing of Ki by 2 and of Kj by minus 2. So this is exactly what was illustrated in the light bulb trick for 2 components, as I showed before. So the important thing is that even though Dehn homeomorphism, that this Dehn homeomorphism changes the framing of the link, this is invisible in the framing Skein module, which does not see which component is being twisted. Okay, and therefore what happens is that these twists, they cancel out algebraically in the framing Skein module. So what happens is that what we actually need is that LF should only be composed of links which do not intersect any two sphere in M transversely at exactly 1 point and not 2 points. Okay. So this completes the proof for the structure of the framing Skein module. So a corollary of this theorem is as follows. We have an epimorphism from the framing Skein module to the group ring over the first homology with Z2 coefficients. And this epimorphism is not canonical and depends on the choice of spin structure of M. So if you recall, we had a homomorphism from the first homology of M with Z2 coefficients into Z2. So if we name this map, say B, then this epimorphism omega of K is the homology class of K if B of the homology class is 0, and omega of K is Q times the homology class of K if B of the homology class of K is 1. And here K is a frame knot in the manifold. Okay. Now we come to connections to other Skein modules. The first is the connection to the Kaufman-Brackes Skein module. So what is the Kaufman-Brackes Skein module? Well, you consider linear combinations of ambient isotopy classes of unoriented framed links in an oriented 3 manifold, modulo the Kaufman-Bracket expressions. This is the Kaufman-Bracket Skein relation, and this is the trivial component relation. So the Skein relation is L plus minus AL naught minus A inverse L infinity. And the trivial component relation is the usual one as we have. And L plus L0 infinite and L infinity are 3 diagrams which are exactly the same everywhere except for in the neighborhood of this crossing where they differ as shown. Okay, so when you mod out by the Kaufman-Bracket expressions, you obtain the Kaufman-Bracket Skein module. One thing to note is that if the ring R is the ring of Laurent polynomials with integer coefficients in the variable A, then we remove the qualifiers R and A. Okay, so in this proposition, we have an epimorphism from the Kaufman-Bracket Skein module of a 3 manifold M over the ring of Laurent polynomials with integer coefficients into this group ring over the first homology of M with Z2 coefficients. And again, just as before, this epimorphism is not canonical and it depends on the choice of spin structure on M. And the codomain of this map is called the spin-twisted homology. Okay. Next is the connection to the Q homology Skein module. So this Skein module is defined as follows. So you consider linear combinations of ambient isotopy classes of oriented framed links in M, modulo the Q homology Skein relation L plus minus QL0, and the Q homology framing relation L1 minus QL. And modding out by these framing expressions and, modding out by these Skein expressions and the framing expressions gives us the Q homology Skein module, which is also known as the second Skein module. Okay, and just as before, we have an epimorphism from the Q homology Skein module into the group ring over the first homology of M with Z2 coefficients. And again, this epimorphism is not canonical and it depends on the choice of spin structure on M. So this diagram over here summarizes the 3 propositions. So we have an epimorphism from the Q homology Skein module into this group ring. We have an epimorphism from the framing Skein module into this group ring. And we have an epimorphism from the Kaufman-Brackes Skein module into this group ring. And these 2 group rings are related by the substitution Q is negative A cube. Okay. So we have spoken about torsion in the framing Skein module, and we've also mentioned that the Kaufman-Brackes Skein module has torsion when the manifold has a non-separating torus or 2 sphere embedded in it. So we conjecture that this is the only case in which torsion can arise for the Kaufman-Brackes Skein module. So we conjecture that if an irreducible compact-oriented three-manifold M is non-Haken, then the Kaufman bracket three-manifold is torsion-free. And if a compact-oriented three-manifold contains an incompressible two-sphere torus, which is non-parallel to the boundary, then the Kaufman bracket Skein module contains torsion. Okay. So we will combine this conjecture with the following theorem, which was originally Witten's finiteness conjecture, but this was proven by Gunningham, Jordan, and Safronov last year in August. And the theorem says that the Kaufman bracket Skein module for any closed oriented three-manifold over the field of rational functions in the variable A is always finite dimensional. So we will combine this theorem. So we combine this theorem with the conjecture on the previous slide to obtain the following conjecture, which says that the Kaufman bracket Skein module of a closed oriented irreducible non-Haken three-manifold has finite rank. Okay, so this finishes my talk. This is the paper. It is up on archive. If you would like to connect with me, or you want to discuss this paper or any of my other work, or just talk about mathematics, please feel free to contact me on my email ID, rhea_palak@gwu.edu. I would be happy to speak with you. Thank you for listening. Bye-bye.